In today's session, we are going to solve a few questions based on area proposition of similar triangles. We know that the ratio of areas of similar triangles is equal to the square of the ratio of their corresponding sides. So using this idea, we are now going to solve a few questions. Let us take a look at the first question. Prove that the area of the triangle BCE described on one side BC of a square ABCD. So we need to draw a square. Let us label the square as ABCD. So ABCD is a square. Prove that the area of triangle BCE described on one side of the square is equal to 1/2 the area of similar triangle described on diagonal AC as the base. So there is a triangle which is described on BC as the base. There is a triangle BCE. So this is triangle BCE. And there is another similar triangle which is described with AC as its base. So I can draw AC. AC is now going to be the base. And I'm going to draw a triangle which is similar to the given triangle. Okay. So triangle ACF, let us name this particular point as F. Let us now understand what is given with respect to the diagram. It's given that, so let us note down, we are given a square ABCD. Triangle BCE, it's given that triangle BCE is described on one side BC of the square is equal to area of the similar triangle. So basically triangle ACF, the triangle ACF is similar to triangle BCE. So it's given that these two triangles are similar, triangle ACF. Now we have to prove that the area of triangle BCE is equal to 1/2 the area of triangle ACF, right? This is what we have to prove. Now we know that, so now let us write the proof. We know that it's given that triangle BCE is similar to triangle ACF. So how do I know this? Because it is written here that triangle BCE is described on the side BC and it is similar to the triangle ACF, right? So therefore I can say that area of triangle BCE divided by area of triangle ACF, I know that as these two triangles are similar, the ratio of their areas is going to be the square of their corresponding sides. So the corresponding sides are BC and AC. And now if I consider the side BC as x, so let BC be equal to x, then I know that this is a square. So this implies that AB is also going to be x because this is a square. So in a square all sides are equal. And I also know that angle B is a 90. So angle B is equal to 90 degree, which means that using Pythagoras, I can say that AC square is equal to AB square plus BC square, which means this equals x square plus x square. And therefore I can say that AC square is 2 times x square, and therefore AC is equal to square root of 2 times x. So this particular length is root 2 times x, and therefore now I know that BC is x and AC is square root of 2 times x the whole square, of which the term x and x cancels, and therefore this becomes 1 upon root 2 the whole square, and 1 upon root 2 the whole square is equal to half. Therefore, I can say that area of triangle BCE divided by area of triangle ACF is equal to half, and this implies area of triangle BCE is equal to half of area of triangle ACF. And this is precisely what we wanted to prove. So again, just to summarize, we took a square. On the side BC, I drew a triangle BCE. With AC as the base, I drew a triangle ACF. It was given that the two triangles are similar. So because the triangles were similar, I was able to use the area property for similar triangles. And then using Pythagoras theorem, I assumed AB as x and BC as x. I found out AC using Pythagoras theorem. And then I found the ratio of the areas by substituting BC and AC, and I got area of BCE is half the area of triangle ACF. So this is how I approached this question. Pausing for a minute before we take up the next one. Moving on to the next question. Prove that the area of the equilateral triangle described on the side of a square is half the area of equilateral triangle described on its diagonal. So let us draw a square. We have to show that the area of an equilateral triangle described on the side of the square. So this is an equilateral triangle which is described on side BC of the square. Let us label the sides. So A, B, C and D. So the vertices are labeled as A, B, C, D. Let this be E. This is an equilateral triangle. This is given to me. Therefore, every angle is equal to 60 degrees. And we have to show that the area of this equilateral triangle is equal to half the area of an equilateral triangle which is described on the diagonal AC. So ACF is an equilateral triangle which is described on the diagonal AC, and BCE is the equilateral triangle which is described on side BC. So it's given that this complete angle is equal to 60 degrees and angle ACF is also equal to 60 degrees, simply because triangle ACF is an equilateral triangle. So let us write what all is given here. It's given that ABCD is a square. ABCD is a square. Then it is given that triangle BCE is equilateral triangle, and triangle ACF is also an equilateral triangle. And now we want to prove that. So let's say to prove area of triangle BCE is equal to half the area of triangle ACF. So if you think about it, there are various ways of proving this particular problem. Let us use the concept of similar triangles. So I know that because angle B, or rather angle CBE is equal to angle CAF, and also I can also take angle BCE equal to angle ACF, I can say that these two triangles are similar by the AA test, right? So I can say consider triangle BCE and triangle ACF for similarity. I know that angle CBE is equal to angle CAF, which is equal to 60 degrees, and similarly angle BCE is equal to angle ACF, which is also equal to 60 degrees, because the triangles are equilateral. And therefore I can say that triangle CBE is similar to triangle ACF by the AA test of similarity. And therefore area of triangle CBE divided by area of triangle ACF is going to be equal to the square of the ratio of their corresponding sides. Now because ABCD is a square, I can take this particular side as x and this particular side as x, and by Pythagoras theorem AC will be root 2 times x. Therefore this is going to be CB is equal to x and AC is equal to square root of 2x the whole square, and that is going to be x square by 2x square, and therefore I can say that area of triangle CBE divided by area of triangle ACF is equal to, now over here you will notice that x square and x square cancels, and you basically get 1 by 2, which means that area of triangle CBE is equal to half the area of triangle ACF. So this is one way by which you can prove this particular problem. I will pause for a few seconds before I go ahead and show you another way, and that another way is going to depend upon the formula for area of an equilateral triangle. Okay, so let us use the formula for area of an equilateral triangle. So if you consider triangle BCE basically has its side equal to x, BC is equal to x, and I know that area of an equilateral triangle is given by root 3 upon 4 times side square. Therefore area of triangle BCE is going to be square root of 3 by 4 times x square, right? Similarly, area of triangle ACF is going to be, so if you think about triangle ACF is built on base AC, and the length of AC according to Pythagoras theorem is square root of 2 times x, and therefore its area is going to be root 3 by 4 times square root of 2x the whole square. Now if I take the ratio of these two areas, so area of triangle BCE divided by area of triangle ACF, this is going to be root 3 upon 4x square divided by root 3 upon 4, and root 2 square is 2x square. Now root 3 upon 4 cancels, x square and x square also cancels, so 2 is left in the denominator, and therefore area of triangle BCE, so I can say that therefore area of triangle BCE is equal to half the area of triangle ACF. right? This is how I can go about this particular question. So again, pausing for a few seconds before I take up the next one. Moving ahead, let's take a look at the following question. Equilateral triangles are drawn on the sides of a right angle triangle. So let us draw a right angle triangle. On this right angle triangle, equilateral triangles are drawn on all the sides. So this is the equilateral triangle drawn on the hypotenuse. This is the equilateral triangle drawn on one side. And there is one more equilateral triangle drawn on this particular side. Right? So let us label all the vertices. Let us consider ABC to be our right angle triangle, which is right angled at B, of course. So this is our original triangle. On all the sides of this triangle, I have drawn three equilateral triangles. So PAPC is one equilateral triangle, AQB is the other equilateral triangle, and BRC is the third equilateral triangle. So all these are equilateral triangles. Now what I have to do is, I have to show that the area of the triangle drawn on the hypotenuse, that is area of triangle APC, I have to show that area of triangle APC is equal to the sum of the areas of triangles on the other two sides. So I have to show that this equals sum of area of triangle AQB plus area of triangle BCR. This is what I have to prove in this particular problem. So please note that all these triangles are equilateral, which means that all angles in these triangles is equal to 60 degrees, right? So all the angles are 60 degrees. And therefore, I can say that all the three triangles are similar to each other, correct? So I can say that triangle AQB is similar to triangle APC, and of course I can prove this using the AA test. And also I can say that triangle BCR is similar to triangle ACP, again by the AA test, because all angles happen to be 60 degrees. Therefore, if I now think about the relation of their areas, I can say that area of triangle AQB divided by area of triangle APC, this is going to be equal to the square of their corresponding sides. So I can write this as AQ upon AP the whole square, right? And also area of triangle BCR divided by area of triangle APC, the ratio of the areas of these two triangles is also going to be the square of the corresponding side. So this is going to be BC upon AC. And over here in the first relation also, you can think of taking the ratio as AB divided by AC, right? Because the sides are all equal to each other. So whether you take AQ or AB, and whether you take AP or AC, it really doesn't matter. So we have these two relations now, and what I'm now going to do is I'm going to add up these two relations. Because I noticed that the denominator is area of triangle APC, it will be very easy to add these fractions. So I can say that area of triangle AQB divided by area of triangle APC plus area of triangle BCR divided by area of triangle APC is equal to AB square by AC square plus BC square upon AC square, and that is equal to AB square plus BC square divided by AC square. Now I can definitely use Pythagoras theorem. Pythagoras theorem will say AB square plus BC square is equal to AC square divided by AC square, which equals 1. And therefore area of triangle AQB plus area of triangle BCR, the whole divided by area of triangle APC is equal to 1, because on the right hand side you will notice that I applied Pythagoras theorem and I got the ratio of the two sides as 1. And this implies that area of triangle AQB plus area of triangle BCR, by cross multiplying, taking the area of triangle APC to the right hand side, I get area of triangle AQB plus area of triangle BCR is equal to area of triangle APC. And this is exactly what I had to prove, and therefore hence proved. So what I simply did was I showed that the triangles were similar to each other. So first I took these two triangles, I showed that they are similar, and that is how I got the ratio of their areas equal to the square of the ratio of their sides. That is how I got the first relation. And then I picked up the next two pairs of triangles, that is these two triangles. I again showed that they are similar according to the AA test, and therefore the ratio of their areas was the square of the ratio of their corresponding sides. And then simply adding the two equations, I applied Pythagoras theorem in the numerator, and I got area of AQB plus area of BCR, the whole divided by area of APC was equal to 1. And cross multiplying area of APC to the right hand side, I got area of triangle AQB plus area of triangle BCR is equal to area of triangle APC. This is how I went about solving this particular problem. Now we can solve the same problem again using Pythagoras theorem. I will show you a different way where we will use the formula for area of an equilateral triangle to solve the same problem. Pausing for a minute while you take a look at this approach. So now I can solve the same problem using the formula for area of an equilateral triangle. Let us assume that the sides are A, B and C. So the area of triangle AQB, because AQB is an equilateral triangle and the side of AQB is A, the area of AQB is given by √3/4 times the side square. Similarly, area of triangle BCR is given by √3/4 upon √3/4 times B square, where B is the side of the equilateral triangle. And therefore, if you add area of triangle AQB plus area of triangle BCR, that is going to be root 3 upon 4 times A square plus root 3 upon 4 times B square. Of course, I can take root 3 upon 4 as common, so you get root 3 upon 4 times A square plus B square, right? Because root 3 upon 4 is common. And now using Pythagoras theorem, so in this triangle, if I apply the Pythagoras theorem, because triangle ABC is right angled, I can now apply Pythagoras theorem and I can say that A square plus B square is equal to C square, right? This is after applying Pythagoras theorem. And therefore, this becomes root 3 by 4 times C square. And that is nothing but the area of the equilateral triangle, APC. Therefore, the sum of the areas of triangle AQB and BCR is equal to the area of equilateral triangle APC. This is how I can prove this particular problem. So we saw two approaches to solve this particular problem. One was using the similar triangle properties, and the other was just using the formula for area of an equilateral triangle. Pausing for a minute. Let's take up the next question. Let's take a look at the following question. In a trapezium ABCD, O is where the diagonals intersect. AB is equal to 2 times CD and AB is parallel to CD. So let us make a diagram quickly. We have a trapezium in which the length of AB is twice the length of CD and AB and CD are parallel to each other. So I can label the vertices. So this is AB and we have AB parallel to CD. So these two sides are parallel to each other. And AB is 2 times DC. That means if DC is X, AB is 2 times X. So I can say that if CD is equal to X, then I can say that AB is 2 times X and O is where the diagonals intersect. So let us draw the diagonals. These DB and CA are the diagonals and O is where the diagonals intersect. We have to find the area of triangle COD, that is we have to find the area of this triangle. If it's given that the area of AOB is 84 square centimeters. So this area is 84 square centimeters. Now we have to find the area of triangle COD, right? So now you could consider, because DC and AB are parallel, I know that angle BAO is equal to angle DCO because of the alternate interior angles, right? So these two angles are equal to each other. Because they are alternate interior angles and the lines are parallel. And also the vertically opposite angles are equal, and therefore by AA test, I can say that these two triangles are similar to each other. So I can say consider triangle DOC and triangle AOB for similarity. So I can say that angle DOC is equal to angle BOA because these are vertically opposite angles. And also angle DCO is equal to angle BAO because these are alternate interior angles. And therefore triangle DCO is similar to triangle BAO because of the AA test, of similarity. And now because these two triangles are similar, I can find the ratio of their areas. So area of triangle DCO divided by area of triangle BAO, this is going to be the square of, you could divide the corresponding sides, that is DC upon BA the whole square. The reason being, areas of similar triangles proposition, or you can also write the complete property saying that ratio of areas of two similar triangles is equal to the square of the ratio of corresponding sides, right? You could also mention the property. And now we know that the area of triangle AOB is known. Area of triangle AOB is equal to 84. And we know the ratio of DC upon BA. So this is how we can find area of triangle DCO. So therefore area of triangle DCO divided by area of the complete triangle is 84 is equal to DC is x divided by AB is 2x the whole square. Therefore area of triangle DCO divided by 84 is equal to, now on the right hand side you will notice that x and x cancels and this becomes 1 upon 2 square, which is equal to 1 upon 4, which implies area of triangle DCO is 1/4 of 84, which is equal to 21 square centimeters. So the area of this triangle is going to be equal to 21 square centimeter, right? This is how I can find the area of COD. So again over here we proved that the two triangles are similar by using the AA test, and then we found the area of triangle DCO using the similar triangles area proposition. Moving on to the next question. So let's consider the following question. ABCD is a trapezium in which AB is parallel to DC and AB is 2 times DC. So let us quickly draw a trapezium. And O is where the diagonals intersect. So let's quickly make that diagram. All right. So we have AB. AB is parallel to DC. So we have ABCD is a trapezium. AB is parallel to DC. It's given that AB is 2 times DC. That is, if DC is x, I can take AB as 2x. So I can say if CD is equal to x, then I can say that AB is equal to 2 times x. And O is where the diagonals intersect. Determine the ratio of area of triangles AOB and area of triangle COD. O is where the diagonals intersect. So now what I can do is I can again consider these two triangles for similarity. So these two angles are equal because of vertically opposite angles. Similarly, these two angles are also equal because of alternate interior angles. So I can say consider triangle DOC and triangle AOB. I know that angle DOC is equal to angle AOB because of vertically opposite angles. And similarly, angle DCO is equal to angle BAO because of alternate interior angles. And therefore, triangle DOC is similar to triangle BOA by the AA test of similarity. Now the ratio of these areas, so therefore area of triangle AOB divided by area of triangle. So if I write AOB is similar to COD, and therefore I need to write area of COD is equal to the square of then ratio of corresponding sides. So I wish to take the sides AB and CD because that relation is known. So this is again according to the similar triangles area proposition. Or of course I can state the complete property which says that ratio of areas of similar triangles is equal to the square of the ratio of their corresponding sides, and therefore I can say that area of triangle AOB divided by area of triangle COD is equal to AB is 2x and CD is x the whole square. And now I know that x and x cancels and therefore 2 square. So I can say that area of triangle AOB divided by area of triangle COD is equal to 2 square. 2 square is equal to 4, and therefore the ratio is going to be 4:1. So I can say that area of triangle AOB is to area of triangle COD. The ratio of these two areas is equal to 4:1. So this is how I can solve this particular question. Again, pausing for a couple of seconds before moving on to the next one. Taking up the next question, it's given that DEF are the midpoints of the sides BC, AC and AB. So let us draw a diagram. So this is basically triangle ABC. This is triangle ABC. It's given that D is the midpoint of BC. So let's mark D right over here. D is the midpoint of BC. Then E is the midpoint of AC. So E is the midpoint of AC. And F is the midpoint of AB. Now if you join these 3 points, we now have to find the ratio of area of triangle DEF and triangle ABC. So we have to find the ratio of area of triangle DEF to the complete area of triangle ABC. So if you think about it, over here I can apply the midpoint theorem, correct? Because F and E are the two midpoints. So I know that AF is equal to FB and AE is equal to EC. So I know that according to the midpoint theorem, I can state that FE is going to be parallel to the side BC. And now if I want to find the area of the triangle DEF to ABC, I should first check whether these two triangles are similar to each other. So you will notice that you can apply the midpoint theorem and say that DE is also parallel to AB. So if you consider FEDB, FEDB is a parallelogram in which the two opposite pairs of sides are parallel, which means angle B will be equal to angle E. Similarly, EFDC is also a parallelogram because EF is parallel to DC, and side DF is going to be parallel to EC. Therefore, I can say that EFDC is also a parallelogram, and opposite sides of a parallelogram are equal. So I can say that angle C is equal to angle F. And similar theory can be even applied for angle A. So angle A will therefore be equal to angle D, right? So I can say that I can first state the parallel parts using the midpoint theorem. So using midpoint theorem, I was able to state all these three properties, 1, 2 and 3. I showed that the lines were parallel, and that is how I concluded statement number 4, which said that I had a lot of parallelograms in this diagram. And therefore, I was able to conclude that angle DFE was equal to angle C, angle DEF was equal to angle B, and angle FDE was equal to angle A, right? So this was equal to angle A, this was equal to angle C, and this is equal to angle B. And therefore, by the AA test of similarity, I can say that triangle DEF is similar to triangle. So D corresponds to A, E corresponds to B, and then I have C. So triangle DEF is similar to triangle ABC, and therefore area of triangle DEF divided by area of triangle ABC is equal to DE upon AB the whole square, right? DE upon AB the whole square. But I know that DE, according to the statement 3, I know that DE is half of AB. So I can write this as half of AB upon AB the whole square. And therefore, area of triangle DEF divided by area of triangle ABC is equal to AB cancels, and half square is going to be 1 by 4. And therefore, the area of triangle DEF is 1/4 the area of the whole triangle. Rather, according to the property of midpoint theorem, in 9th standard or in earlier years, you must have learned that the line joining all the three midpoints divides this particular triangle into 4 equal parts, and that is why the area of triangle DEF is 1/4 the area of the whole triangle ABC. So this is how we can solve this particular question. Let me pause for a minute while you take a look at all the properties that were used in this problem, and then we shall continue. Moving on to the next question. Let's consider the following question. Two isosceles triangles have equal vertical angles. So let us draw two isosceles triangles having the same vertical angle. So right now you will notice that these two isosceles triangles have the same vertical angle, right? So let me label the isosceles triangles as ABC and DEF. I know that these vertical angles are equal, so angle A is equal to angle D, right? This is known. So these two angles are equal to each other. Now they have equal vertical angles and their areas are in the ratio 16:25. We need to find the ratio of their corresponding heights. So now if you consider triangle ABC, this is an isosceles triangle. So let us consider these sides to be X and let the sides of triangle DF be Y each, right? These are two isosceles triangles. So before I can use the property for areas, I first need to prove that these two triangles are similar. So the way I can do it is I can say AB upon DE is equal to X upon Y and AC upon DF is also equal to X upon Y, and at the same time angle A is equal to angle D. Therefore, we have two sides which are in the same proportion. So I have AB upon DE is equal to the length AC upon DF, and the vertex and vertical angle is also equal. Therefore, by the SAS test, I can say triangle BAC is similar to triangle EDF, and this is by the SAS test. Correct? And therefore, I can say that area of triangle BAC divided by area of triangle EDF is going to be equal to the square of the ratio of their corresponding sides. That is BA upon ED the whole square, and this is by the area proposition. This is by the area proposition for similar triangles. Right? And it's given that the ratio of the areas is 16:25. Right? So 16/25 is equal to BA by ED the whole square. Now, by the way, over here, it looks like I should have taken the area of EDF to BAC as 16:25 because EDF is the smaller triangle. But again, this is because I have drawn it like that, right? So over here, it really doesn't matter. I can still take ABC by DF as 16:25, and I just need to make the triangle DEF bigger, right? Therefore, this implies that BA upon ED is equal to 4 upon 5, taking the square root on both sides. And therefore, the ratio of sides of these triangles is 4:5. And we know that since the triangles are similar, I can say that the ratio of their sides is going to be equal to the ratio of their corresponding altitudes. Right? And the ratio of the sides is 4:5, and therefore the ratio of corresponding altitudes is also going to be 4:5. So this is how I can solve this particular question, pausing for a couple of seconds. Moving on to the next question. It's given that D and E are points on AB and AC respectively, such that DE is parallel to BC. And DE divides the triangle into two equal parts area wise. That means the area of triangle ADE is equal to the area of DEBC, right? The area of this triangle ADE is equal to the area of the quadrilateral or area of trapezium. This is going to be a trapezium BDEC. We have to find the ratio of BD is to AB, right? So let me highlight the ratio of, let me highlight the sides whose ratio needs to be found. We need to find the ratio of BD to AB, right? This is what we need to find. So let us now consider these two triangles for similarity. I know that because the areas are equal, so if this is area A, area of ABC, area of BDEC is also A. So I can say that let area of triangle ADE be equal to A, and this would imply area of the trapezium BDEC is also equal to A, and that implies area of triangle ABC is going to be 2 times A. That is, the area of the whole triangle is going to be 2A. Now I can prove triangle ADE is similar to triangle ABC. So consider triangle ADE and triangle ABC. I can say that angle A is equal to angle A because it is the common angle. I can also say that angle ADE is equal to angle ABC because these are the corresponding angles, and therefore triangle ADE is similar to triangle ABC because of the AA test, correct? And because these are similar, I can say that area of triangle ADE divided by area of triangle ABC is going to be AD upon AB the whole square. Now I know that these two areas are in the ratio 1:2 because area of triangle ADE is A. According to our assumption, we took the area of triangle ADE as A, and we concluded that area of triangle ABC is going to be 2A. So A by 2A is equal to AD by AB the whole square, and this implies that AD upon AB, so here A and A cancels, is equal to 1 upon 2 the square root, which implies, so now I can say that AD upon AB is therefore equal to 1 by root 2, which means AB is square root of 2 times AD, right? So if I take AD as X, if I take the length of AD as X, let AD be X, then this implies AB is root 2 times X. And therefore BD is going to be AB minus AD, right? I know that AB is root 2x minus AD is X. Therefore this is going to be root 2 minus 1 times X. And now if I want to find the ratio, so what am I supposed to find? I want to find BD upon AB. The length of BD is root 2 minus 1 times X divided by the complete length of AB is root 2x. Now x cancels, and therefore BD upon AB is root 2 minus 1 upon root 2. This is what I was supposed to find, and this is how I solved this particular problem. So again, just to recap quickly, I noticed that the triangle and trapezium have the same area. So I was able to find the area of the whole triangle, and then using the similar triangles proposition, I was able to find the ratio of the sides, and that is how I reached the conclusion that AB is root 2 times AD. And then I applied the common ratio. I took AD as X and AB was therefore root 2x. Then I went ahead and I found the value of BD, and then I took the ratio and I got root 2 minus 1 upon root 2. This is how I can solve this particular question. So we end our today's session here. I will pause on this question for about a couple of minutes and then we end this session. Ending today's session here.